Hi, David. Thank you very much. And thank you for the opportunity to give this talk, and thank you for everyone who's managed to log in. I have a few of my colleagues in the room as well watching me. Okay, so I should just say before I start, let me turn off my volume because I'm getting some feedback. Yeah, I turned off my volume, so if anyone has a question, please wave at me. So before I start, I should say a lot of what I'm going to talk about is work originally due to the people you see on the bottom of the screen, Sheehan Olver, who's now at Imperial, where I did my undergraduate degree, and Alex Townsend, who's at Cornell now. We were colleagues at Oxford for a time. So the ultraspherical method, the original ultraspherical method I'm going to talk about was introduced by them a few years ago. But recently I've been working with both of them on some extensions of the method, and that's what I'm going to talk about in the second half of this talk. So I realized this morning spectral methods mean different things to different people, so I should have maybe specified I'm interested in numerical solutions to differential equations. And whenever you start a talk or you write a paper on those things, you start off with this first paragraph, justifying that ODEs and PDEs are everywhere, modeling physical phenomena in science and engineering, and well, we need to solve these things, and quite often there aren't closed form solutions. Right? Either they're unavailable, we know there is no closed form, or it's very hard to compute the closed form of the solution. And there are ways around this. People might use symmetries to try and solve these equations, or approximations. But what I'm interested in is finding approximate solutions using numerical methods. And of course, there are a variety of numerical methods that we might appeal to. And I've listed a few of those here. So the first ones you see in blue are typically the ones that we teach at undergraduate level. So these are finite difference methods, finite element methods, maybe finite volume methods, if you're doing things in computational fluid dynamics. And I've just tried to summarize in 4 or 5 words the properties of those. So typically they're local methods. That typically means that we end up with sparse matrices when we end up doing these discretizations. They're very flexible. So if you want to try and do these in higher dimensions in multiple geometry, in complicated geometries, that's reasonably straightforward to do. It can be done. The downsides, though, are that they typically only give low-order convergence or slow convergence. So if we're looking for 10 to 15 digits of accuracy in our solutions, and that's what I'm going to talk about a bit later, it's going to be difficult to try and get that level of precision with these methods. Something else we maybe sometimes teach at undergraduate level is Fourier and Laplace transform techniques, which can work very well, and we can get that kind of accuracy using those. And I list these under numerical methods because for practical problems, there's normally some numerics involved in doing the inversion of those transforms. But those are typically used when the domain is periodic or unbounded, and that's not what I'm interested in here. I'm interested in finite domains. So boundary value problems on finite domains, those aren't really going to be as useful. So that brings me to spectral or pseudo-spectral methods. I'm really going to talk about spectral methods, which are Galerkian or coefficient-based approaches. Pseudo-spectral methods are what we call collocation-based approaches. They're both very similar in nature. I don't really want to talk too much about the details, but it's just I'm going to focus on spectral methods. And what are the properties of these? Well, they're global in nature. So this usually means we end up with dense matrices, particularly with the collocation matrices, collocation approaches. But what I want to talk about today with these ultraspherical methods is a way of getting sparse matrices when we do spectral methods. And the other thing that characterizes these spectral methods is that they're high order in accuracy, so we can typically get very fast convergence using very small discretizations. So that's sort of the opposite end of the spectrum to the finite difference, finite element methods, where we have low order accuracy. Here we're getting very high order convergence, typically geometric if the solution is smooth enough. So yeah, that's the aim. I want to try and get high accuracy solutions to boundary value problems on finite domains. And to do that, I'm going to try and use spectral methods. Okay, so the outline of my talk to talk you through this is, well, I don't assume that everyone here knows what a spectral method is, so I'm going to spend roughly 1/4 of the time devoted to introducing the classical Chebyshev spectral methods. There are other kinds of spectral methods, so Fourier spectral methods would be the other one, but I'm going to focus on Chebyshev methods, just give you a brief introduction to those. Then I'll spend a little bit of time talking about the ultraspherical method as was introduced by my former colleagues, Sheehan and Alex Townsend, to give you an idea of how that works. And then in the second half of the talk, I'll talk about two of the extensions of this approach I've been working on recently, namely for integral differential equations and fractional differential equations. keep things simple, we only have 40 minutes to go through this. I'm going to focus on the most simple cases of these equations. In particular, I'm going to be looking at linear equations in one dimension for the ODEs, IDEs, and FDEs, and I'm just going to look at the case where we have constant coefficients. But the methods I discussed can quite readily be extended to the more complicated cases where we have systems of equations, or maybe we have PDEs in regular geometries, or if those constants if those coefficients are non-constant. Okay, so as I said, the first thing I want to talk about is introducing the sort of classical Chebyshev spectral method. And these were pretty much introduced by Stephen Orszag in the late 60s, early 70s, and there's a picture of him now. And I think what really excited people about these methods at the time was where you can see the computers they were using there back in those days. And at that time, they'd really got dense linear algebra sorted. They had good algorithms for doing dense linear algebra. Sparse linear algebra was still coming onto the scene. So what was attractive about spectral methods was that you could use these to discretize problems, end up with a dense system that you knew how to solve well, and you could still get high accuracy. It's maybe not the case these days. Things have advanced, but that's where the basis of these methods came from. So how I want to introduce spectral methods is to talk actually about something which we do usually discuss at undergraduate level, and that's a power series solution for differential equations. Here's a boundary value problem. Here's a boundary value problem. This is going to be the problem I'm going to focus on for most of this talk. Again, as I said, it's a very simple problem. We could extend the approaches to more difficult problems quite straightforwardly, but for ease of discussion, let's focus on this. So second order boundary value problem. Okay, so how do power series solutions work? What do we teach our undergraduates? Well, we're going to assume, and we'll come back to this later, that we can expand both the right-hand side, F, and the unknown solution U as a power series, and let's say about the origin. So here's my
I hope you can hear me there. Nick unfortunately got disconnected, and you'll be back shortly.
Oh, okay, no problem.
Am I back? Great. Okay, sorry about the disruption. Okay, so let me repeat what I said. We're going to assume that we can expand the right-hand side of our equation as F as a power series, and the unknown solution also as a power series here. Now, if we had a power series of U, we could easily differentiate that power series. We just need to differentiate each of the terms if it's about a power series, and we would end up with these for the first derivative and the second derivative. So what we're going to do then is we're going to take those expansions, substitute it to the boundary value problem we're interested in, or at least the differential equation we're interested in, and we're going to equate the coefficients. So I'm going to collect all my powers of x, and I want to make sure that my left-hand side for each power of x is equal to my right-hand side. Equate the coefficients. And in this case, for the equation we're interested in, we would end up with something like this. So now if this was an initial value problem, so suppose we were given the value of the solution at the origin and maybe the value of the derivative at the origin, this would tell us how to solve this. So Those two pieces of information would tell us U0 and U1, and this relationship here would then tell me how to compute, say, U2. And then I could use the next iteration of that to compute U3, and I could compute all the coefficients in the power series of my solution. That's not quite the situation we're in here. Here we're looking at a boundary value problem, so I don't have those two initial conditions to give me U0 and U1, but I do have some other constraint that I can add to my coefficients of the solution, and those are here. So in our problem, we said the boundary condition at the left and the right was equal to 0, and so this would be the condition we would have on the coefficients in that case. Oops. So if we take that relationship we had on the previous slide, it's a linear relationship, and actually we could write it down in matrix form. And if we did that, we would end up with this matrix here. It's an infinite dimensional matrix, right? Those power series, they sum from n from 0 to infinity, so this matrix in principle goes on forever. We'll talk about that in a second. The other thing, or the main thing I want to talk about is the fact that it's almost banded. So a banded matrix would have entries only around the diagonal, which is almost what we have here. That's the name. The thing breaking that is we have these two dense rows at the top, which complicate things slightly, but we could still solve this linear system very efficiently using, for example, the Sherman-Morrison formula or something similar. So we could do that. We could say, well, I don't want to solve this infinite dimensional linear system. That would be very difficult to squeeze onto our computer memory, but we'll truncate at some size n. We'll end up with a matrix. We could then solve that efficiently. We would get approximate solution of the coefficients, and that would be our numerical solution. And just to show you, here's a MATLAB SPI plot of that matrix. So for those of you who aren't familiar, in MATLAB, if you have a matrix and you type SPI of the matrix, it shows you such a picture. And the blue dots represent where there's a non-zero entry of the matrix. So here we're again seeing the almost banded nature of this discretization. And so what I did was I solved this linear system that gave me the power series coefficients, or the approximate coefficients in the power series of the solution. I could then plot my approximation here, and it looks something like a cosine, which you would expect for this BVP. And here's the decay, or the convergence of the approximation. So n is the size at which I chose to discretize the matrix. So I solved that, and then here I'm plotting the error compared to the true solution in the approximate infinity norm for each value of n. And we see it goes down very fast. We only need this is a 17 by 17 matrix of this form in order to get roughly machine precision accuracy for this problem. So that's great. Why do we need to carry on? Well, there are two problems, it turns out. One is that we made the assumption that we had a valid power series solution of our solution, and it turns out that's not always possible. There's a fairly strict requirement to place on our solution. The second is to do with ill conditioning. There are two forms of ill conditioning. One is in this matrix here. It turns out this matrix in general will be ill conditioned. And what that means is that if we make a small change to this right-hand side here in this vector, so our coefficients of the function f, then we would make a large change in the value of our solution that we put out. So there's one form of ill conditioning that arises when we use this approach. The second is that actually computing these coefficients, power series coefficients, is also ill conditioned, because the basis we're using, those monomials, let me go back. Here our basis is essentially the monomials x to the n. That's also an ill conditioned basis. I'll talk more about that in a moment. Okay, so what's the solution? Well, it says here the solution is we're going to use, rather than the monomial series expansion, we're going to use a Chebyshev series expansion. And I'll get to that in a moment. I just want to introduce, before I do that, some notation for the same problem we just spoke about. Okay, here we go. So this is my notational interlude. So here's the power series solution, or the power series representation of our series we had, solution we had before. And this, again, just suppose it exists. And these were the relationships we had for the derivatives. It turns out I can write these themselves in matrix form, and I'm going to call these things differentiation matrices. So here's the one corresponding to the first derivative, so that's this guy. Here's the one for the second derivative, that's this guy. And what does that mean? Well, if I took these coefficients in this power series and I write them down in a vector like this, these are the power series coefficients of u, then I can get the power series coefficients of the derivatives, again assuming everything was happy enough and they existed, by multiplying by these two matrices. So multiplying the vector u by this matrix would give me the power series coefficients of the derivative, and multiplying by this matrix would give me the power series coefficients of the second. Okay, so this is what I'm going to call differentiation matrices, and we're going to see these kind of matrices arising throughout this talk. not for these monomial bases, but for different kinds of bases. Okay, so again, now we have these, we can form the same almost bounded matrix we had previously just by using this notation, right? So here are my boundary constraints, so it gives me the dense rows at the top of the matrix I had before. And here's our linear operator, so here I'm going to use the second derivative matrix, that's this one, to represent the second derivative, and then this would just be their density matrix, right? That's using the coefficients here, so we end up with this. And this would give exactly the same matrix we saw on the previous slide. Okay, so that's just what I mean when I say differentiation matrix. Okay, so I said there were these two problems with this power series based approach, and we're going to try and overcome these with Chebyshev polynomial expansions. So what is a Chebyshev polynomial? And what do they look like? Well, this is what Chebyshev looks like. He's a famous Russian mathematician. He's often said to be the father of Russian mathematics. But we're actually more interested in what Chebyshev polynomials look like, and here are an example of the first 6, I think, that I plotted. And what do we notice about these? Well, the first thing we want to do is compare these to the monomial basis we just talked about, the basis we were using in the power series, which look more like this. And we see quite a stark difference here between the monomials and the power series, and the Chebyshev polynomials. And what's the big difference? Well, the monomials, they all look like each other, particularly when the degree gets high, ignoring the sort of the negative value. If we look over here, you can imagine as we take higher and higher powers of x to the n, all these things are looking the same. And that's actually what gives rise to the ill conditioning in this problem we're using this basis. When we put them on a computer, it's very hard with rounding error involved to determine exactly what monomial we're talking about, and so those sort of rounding errors get amplified. With the Chebyshev polynomials, they all look very different, and actually the phrase we want to use there is orthogonality. Chebyshev polynomials are orthogonal, and just take that to mean that they look very different from each other, which is going to give us a much better conditioned properties. Okay, so this is one way of defining those Chebyshev polynomials, but it's not very useful in practice. It does us nice theoretical properties. How do we actually compute these guys? Well, it turns out, firstly, there's a nice recurrence relation. So this is convincing us that these are polynomials. If I start with the first two, these are given explicitly here, and the further ones are given by this recurrence relation, it's clear to see that Tn will be a polynomial of degree n. So that's nice, we can compute them that way. It turns out the really nice thing about Chebyshev polynomials is they have an explicit form. So when I show this to my undergraduates, they never believe me that this is a polynomial, but it's quite easy to show. Just some double angle trig formula applied to this thing, you can recover the recurrence relationship, and that shows you that this really is a polynomial of degree n. What's going to be important for us, again, trying to solve differential equations using these Chebyshev polynomials is this formula. And compare this to the differentiation formula we had for the monomials, right? If we have x to the n and we differentiate it, we get x to the n minus 1. We can write down a similar thing for these Chebyshev polynomials, but it's a little bit more complicated. So you see here, if I differentiate t to the n, it involves a bunch of the previous Chebyshev coefficients. But the formula itself is still pretty nice. It's a longer expression. And we'll see what the consequences of that are in just a moment. Okay, so these are Chebyshev polynomials. What are Chebyshev series? Well, we want to approximate our underlying unknown solution u as a linear combination of these guys. That's the Chebyshev series. I don't want to go into too many details, but there are some theorems which tell us how well this series behaves. And it turns out that the convergence requirements to have a convergent series are much less strict than, say, the power series that we would need for the power series solution. And it turns out that if the solution u is just Lipschitz continuous, so it's a little bit more than continuity, a little bit less than continuously differentiable, then this power series converges nicely. And by nicely, I mean it's absolutely and uniformly convergent. So, long story short, it converges nicely. And in fact, we can actually say more. So if the solution has k continuous derivatives, then we can say exactly how fast the magnitude of these coefficients go down, so how well a finite approximation to this will converge. And then the most stronger thing we could say is if the unknown solution u is analytic or holomorphic in some neighborhood of the interval we're interested in, then these coefficients will actually behave geometrically, so that's very fast. So if we have a continuous function, we get algebraic decay in these coefficients. An analytic function, they decay geometrically. And that's going to give us, if we can use these series expansions to do our approximation, it means we can take a very small discretization and still get very accurate approximations. And then just one other property I want to quickly mention in passing. How are we going to compute these coefficients of these series? Well, it turns out that they can be accurately and efficiently computed using what are known as fast Fourier transforms. So they're just, what I'm saying here is there are efficient methods for approximating these coefficients. So both for the solution and for the right-hand side. Okay, so that was Chebyshev Polynomials and Chebyshev Series. How do we put those together to make Chebyshev spectral methods? Well, the idea is almost exactly the same as the power series that we spoke about previously. Just instead of expanding the solution U and F as power series, we're going to expand them as Chebyshev series. Okay, and then we're going to do the same thing as we did before. We're going to equate coefficients. I put a little asterisk here because equating coefficients is one way of thinking about it. What we're really doing is making sure the residual is orthogonal to a certain basis. But for now, we can just think about equating coefficients. It turns out to be pretty much the same thing. So that's what we're going to do. That's our approach. I haven't written down that sort of recurrence relation on the coefficients because it's a little bit more complicated here to write down, mostly because of that formula for the derivative of Tn was a lot longer, and it would be difficult to write that down. But if you write it down in matrix form, here are my differentiation matrices. Right, this is the matrix that corresponds to, if you allow me to go back a couple of slides, back to this formula. Right? If you write this down in matrix form, you end up with this, and you could actually just square this matrix and you would get a second derivative matrix. So now we have all the ingredients we need to make our Chebyshev spectral method. The idea is exactly the same as the power series. We expand U and F as these guys. We'll use this differentiation matrix to approximate the first derivative of the solution, and we end up with a linear system that looks like this. Again, it's in principle an infinite dimensional linear system, but if we know these coefficients are decaying, we could truncate, solve the finite solution, and get an approximation to the solution. So that's it. That's pretty much Chebyshev spectral methods. And so what's the problem now? Why do we still need to continue? Well, the problem is this matrix here, rather than being almost standard as it was in the case of the power series method, this matrix is actually dense. So these coefficients here continue along. And actually, if I do show you a spy plot of this matrix for a larger discretization, it would look something like this. Okay, so in the power series approach, we have this almost standard matrix, which we could solve very quickly. Here, okay, it's not a fully dense matrix, but it's roughly enough a triangular matrix. It's going to be O of n squared operations to try and solve this linear system, which is maybe good enough for some applications. If this was a 25 by 25 matrix, that's no problem. If it was a 2000 by 2000 or a 20,000 by 20,000 matrix, the difference between O of n operations and O of n squared operations is significant. So we want to try and prove that. We want to try and get back to an almost bounded matrix, or use a different representation to give us that. So let's just summarize what we spoke about. We looked at power series methods. What was the downside? Well, we needed a convergent power series, which is a pretty strong assumption to make. And the basis we were using, the monomials, was ill-conditioned. The benefit of using this approach was that we got this almost bounded matrix, which we could invert quickly. We then looked at Chebyshev spectral methods. The advantage was that, well, they were more likely to converge. We had less strict requirements on our solutions for the convergence. The Chebyshev polynomials themselves were orthogonal. It turns out, and I don't get into the details, the matrix itself that we end up with is still a little bit ill-conditioned. We'd like to try and improve that as a downside. The biggest downside of this approach, as far as this talk is concerned, is that the matrix is dense. Right? We have this upper triangular matrix is going to be expensive to solve. So we'd like, obviously, an approach which combines these two and takes the benefits of so we'd like to have nice convergence with orthogonal and well-conditioned matrix and an almost bounded linear system to solve everything. And that's where ultraspherical polynomials come in, and I'll introduce them in a moment, but that's the aim. We want to try and combine the two good parts of these different approaches. Okay, so yeah, this was this idea. It's sort of been visited in the past by various people, but Alex and Sheehan were the first people to write in this in a very detailed way and actually extend the idea to higher order derivatives. What I'm going to show you first is the case of solving first order differential equations, but we'll see later in just a moment that it can be extended to second and arbitrary order differential equations. Okay, so what's the approach? Well, it's a similar idea to this power series kind of method we were doing before, in particular the Chebyshev series approach. But we're going to make a slight twist. We're going to expand our solution as a Chebyshev T series, like we did previously. But we're going to expand our right-hand side as a Chebyshev U series. And we don't actually really need to know what these are. I'll talk about it a little bit. But that's the difference. So rather than expanding both the solution and the right-hand side as Tn, we're going to expand them as two different kind of series. And let me just talk you through the consequences of that. So what we have here are two key ingredients. One is that we have a bounded differentiation matrix, and that's going to give us this almost bounded structure that we need. Okay. So what we have is that if I took my Tn, my Chebyshev Tn polynomial, it turns out if I differentiate that, rather than have that complicated sum of many previous Tr polynomials I had for the differentiation matrix, if I instead express the result as one of these Un Chebyshev second kind polynomials, it's a much simpler relation, right? You just differentiate this, I get n times this one, very much like the derivative of x to the n. And that's going to give me a bounded differentiation matrix. So, okay, let's start off. So we're going to expand our solution as a series in Tn. So it's going to look something like this. Here's my differential equation, just the first order equation for now. So we're going to expand our solution U as the sum of Un Tn of x. We substitute that into our differential equation. So we need to differentiate the first term. Here's that. So, okay, we can move the derivative through the summation sign. We need to differentiate this guy. Use this formula. We end up with this. Okay, so now we'd like to equate coefficients as we did before, but the problem is we're equating the coefficients of, we have two different series here. So I can't equate coefficients of U with coefficients of T, so I need to make sure that I have the same basis in each of these sums. So one thing I could do is I could turn these things back into Chebyshev T polynomials. So that's going to give us back the same situation we were in before, right? That was exactly the situation we had in the Chebyshev spectrum. So the difference here is, instead of turning the U back into a T, so I have all my expression in terms of the Chebyshev T polynomials, well, I'm going to do the other thing and turn my remaining T's also into U's using the second relationship, which I'm calling a conversion relationship, giving me a conversion operator. So whenever I have a T in here now, I'm going to substitute in this expression. And over this. And again, it looks a little bit messy, but if you write it down in matrix form, we notice again that there's a bounded matrix. Right? This is just a short-term recurrence. This only depends on two of these used polynomials, so I end up with almost a bidiagonal matrix. Again, at least it's a bounded matrix. Okay, and this is what we're going to call my conversion operator. So what could we do now? Well, we could just rejig the indices on this, and we could come up with a relationship between each of the coefficients, Un and Fn, very much like we had in that first slide for the power series, which we could then solve to find the solution. And if we write that down in matrix form, we would end up with this. So this D0 would represent my differentiation operator. The S0 is the conversion operator that I needed to convert my Tn's to Un's. So that's why this is appearing here. So this is now our bounded matrix representing this differential operator. And this is the linear system we have to solve. And let's go back and see what I meant by this expression comment here. We're expanding our solution in Chebyshev T, right? That's the first thing we did. And our right-hand side, or I guess more accurately, our residual, is in the Chebyshev U basis, right? Once I differentiated and I've converted, I'm solving everything in U's are now appearing here. So that's why we have to use. So that's the approach, and that's what this Petrov-Galukin thing means. It means we expand the solution in one basis, we look at the residual, or we orthogonize the residual in another basis. And while the benefit of doing that, rather than keeping everything in the Chebyshev T basis, is we ended up with this bounded differential operator. Okay, so let's apply that to an initial value problem, right? So first order differential equation, so I can only have one boundary condition in this case. We'll look at the second order case in a moment. But again, we end up with an almost bounded linear system if I enforce this boundary condition here. So it's almost bounded, so I can solve this linear system very quickly. And again, I said I didn't want to talk too much about the conditioning of the problem of these things, but it turns out we've also solved the ill conditioning of the approach. Most of the ill conditioning was in the dense matrix over here. It turns out by formulating it in this approach with the two different bases, we also improve the conditioning of the problem. So again, this is an infinite dimensional problem, but we could truncate and solve in linear time because it's an almost bounded matrix, and we could approximate our solution well. Okay, so that's first order problems. So of course, we'd like to look at second order or higher order derivatives, and what we need there is ultraspherical polynomials. That's where these come in. So actually, most of the material on this slide is we don't. Well, I just wanted to briefly tell you what ultraspherical polynomials were. Again, they're orthogonal polynomials, so they look different from each other, so they have very nice approximation properties. That's enough for us now. And again, they have very nice recurrence relations, so we can compute them relatively. There are a couple of special cases I just want to mention. These are the Legendre polynomials, which most people have heard of in the context of the Gauss quadrature. They're a special case when we take this parameter lambda equal to a half. And the Chebyshev polynomials I mentioned earlier, they're also a special case where we take this value lambda is equal to 1. So these are the ultraspherical polynomials. They're also sometimes called the Gegenbauer polynomials. This is a feature of Gegenbauer. And they're actually special cases of Jacobi polynomials. This is Jacobi. I included this picture. So this is actually the only known picture of Legendre. It's actually a caricature portrait of him. If you send a picture of Legendre before, or at least you think you have, it turns out that was not a picture of Legendre. For the last 250 years, people have been using a certain picture of a Legendre, but it turns out this was a French politician rather than the mathematician. Someone made a mistake 250 years ago, and that's prevailed until recently, maybe 10 years ago, someone realized, actually, no, this is the wrong guy. So this is the only known portrait of Legendre, which I thought was in. Okay, so these are our ultraspherical polynomials. How are we going to use these to get our higher order derivatives? Well, it turns out those two key ingredients we needed, the banded differentiation matrix and the banded conversion matrix or operator, we also have those for the ultraspherical polynomial. So if we differentiate one of these guys, we end up with a nice simple relationship between higher order parameter space and a lower degree polynomial. So that ends up giving us a differentiation operator that looks like this. The key thing is that it's banded. We also have a similar conversion operator. It looks like this. So they're a little bit more complicated than the one we saw previously for the Chebyshev polynomials, but for these ultraspherical polynomials, we can still get these banded operators. And by combining these in the right way, we can get higher order derivatives. So for example, if we wanted the second derivative of a Chebyshev T expansion, we would multiply D0, which was the matrix we saw earlier, by this one. And we could get the associated conversion operator by multiplying the conversion matrix for the Chebyshev with S1, and that would give us the conversion operator. And what do we notice? Well, each of these operators, so D0 was banded and D1 was banded, so this thing D squared is also banded. If you multiply two banded matrices together, the result will also be banded. Similarly here, these two were banded matrices, so the result, the product of those two will also be banded. So last slide on this ultraspherical method. So now we're going to look at the second order boundary value problem that we discussed at the start. So what's our approach? Well, we're going to expand, as usual, the solution, U in a Chebyshev T series. But now our right-hand side, or more formally our residual, we're going to expand in this ultraspherical basis. Again, we'll equate coefficients in the ultraspherical basis, for boundary conditions. What do we end up with? We end up with an almost banded matrix. Here's the discretization we used just from the previous slide. Maybe it's hard to see because I couldn't put too many entries in this matrix so it wouldn't fit on the slide, but here's a square plot of the matrix. So again, we see we're now solving the second order boundary value problem, the same one as we did with the power series. We end up with an almost banded matrix, which we can efficiently solve, but we've got rid of all those bad properties of the power series solution. And this is actually a nice well-conditioned matrix. Basis we're using is well-conditioned, and we have nice convergence properties because we're using the Chebyshev series. So that's, in a nutshell, what the ultraspherical method is for differential equations. We can extend it to even higher order derivatives. There's no problem doing third, fourth, sixth order differential equations using this approach. We just go to higher parameter ultraspherical polynomial series. Non-constant coefficients can be dealt with. We still can end up with banded matrices in a lot of situations. And PDEs in rectangular domains or straightforward geometries can also be done. Okay, I've been paying attention to time. I'm roughly halfway through. That's fine. So what I want to talk about for the rest of this seminar is the extensions that I've been working on in the last couple of years, both with Alex and Shion, to these ultraspherical methods. And the first of these was extending the method to work with integral differential equations, in particular with convolution type canons. So if you're not sure what that means, here's an example. So on the left-hand side, I have some linear differential operator. It could be more general, but for simplicity, I'm just going to use the same one as I've been using so far in the talk. So this looks very much like what we've been discussing so far. the addition now is that we have this integral operator on the right-hand side. So this one here is what's known as a Volterra integral operator, because we're integrating up to t, which is our independent variable. If we change it to a capital T, which is the end of the domain that I'm interested in, that would be what's called a Volterra operator. And here I'm going to be interested in both of those. In particular, we're interested in convolution type kernels, so that means that this guy here sitting inside the integral operator is of this form. So it's there's some function here. I'm going to assume that it's reasonably smooth. And it takes the form of t minus n. So t is my independent variable, and s is the integration variable in the operator. Right? So this is what we call a convolution type kernel. Okay, so what do I want to do? I want to come up with ultraspherical spectral methods for these kind of problems. So what do I want in particular? Well, I want a fast and well-conditioned linear system. So I mean an almost bounded linear system, and I'd like fast convergence. Well, I know if I can use a Chebyshev series, I would get this. And it turns out I don't want to use the Chebyshev series. The approach I'm going to use here is to use a Legendre series. So what's the approach? Very much like what we did just now with the Chebyshev series, I'm going to approximate solution as a linear combination of Legendre polynomials. I'm going to use almost exactly the same thing as we've been talking about, the ultraspherical method, to discretize the differential operator. So rather than have this Petrov-Galerkin approach that I was talking about just now, we need a Legendre Petrov-Galerkin approach. It turns out to be almost exactly the same. I just spent one slide showing you the differences. That just leaves us with discretizing the right-hand side, and this is the reason why I needed to use Legendre polynomials rather than Chebyshev polynomials in my expansion. It's because we have a nice relationship for the convolution of Legendre series that we're going to use to discretize this, and I'll explain that in just a moment. Okay, so just a brief aside, if you've worked a lot in scientific computing and numerical analysis, people talk about Chebyshev series and use Chebyshev series all the time. Legendre series, not so much. People talk about Legendre almost exclusively in the case of Gauss quadrature, and don't really talk about Legendre polynomials or Legendre series anywhere else. And I wanted to just maybe think about why that is. Here are probably the two answers. The first is that, well, the Chebyshev polynomials and the Chebyshev points, which are either the roots or the extreme of these polynomials, are known in closed form, which is obviously very nice. We saw that nice formula for the Tn in terms of cosine of n, cosine x. The Legendre polynomials we only know via that recurrence relationship, so they're sort of a little bit harder to work with in that sense. And the other connection is the other reason is the connection with the Fourier transform. So it turns out those coefficients can be quickly computed in n log n operations using FFTs. And so historically, I think that's why people were using Chebyshev series, or have been using Chebyshev series rather than Legendre series. But actually, there have been some recent advances, and some of those were due to me. And unfortunately, both of these, they were state of the art at the time, but now people have slightly better methods. I'll have to see if I can improve on those. But Alex and I showed that we can compute those Legendre coefficients in linear time. So it used to be maybe a cubic operation to compute Legendre coefficients, and that can be done in linear time. And the coefficients can also be done in quasi-linear time. So not quite as fast as the Chebyshev coefficients, but still faster than n squared to get n Legendre coefficients. So with these two approaches and the developments that have happened since the papers by Alex and myself, Legendre series are more accessible than they were before. I just want to go to this final point here. Why is that useful? Or was that useful for us? Well, it turns out the Legendre series are also orthogonal polynomials, but the key thing is they're orthogonal with respect to a much more simple weight function, just the weight function 1. Right? So if I integrate two Legendre polynomials from -1 to 1, the result is 0 if the polynomials are of different degree. They're orthogonal with respect to this guy. And this typically sometimes means that we get more convenient expressions and recurrence relations with Legendre series than we do with Chebyshev series, and actually that's exactly the case here with these convolution operators. I'm going to exploit a nice property of Legendre series with convolution operators that will allow us to do these integrated differential equations with convolution kernel. But so first I need to deal with that left-hand side, right? So we needed to now work with the Legendre basis rather than the Chebyshev basis, but the idea is exactly the same. So I'm going to expand my solution as the Legendre series, my right-hand side is some ultraspherical series, and we end up with Again, I won't go through all the steps, but we end up with a banded differentiation matrix, a banded conversion matrix, and we can end up with a fast algorithm to do that. So the idea is almost exactly the same as we saw for the Chebyshev series. We're just going to start with Legendre rather than starting with Chebyshev. There's not much going on. But we managed, Sheehan and I managed to prove that was fine. So actually, the slightly more complicated part is to deal with the right-hand side. How do we deal with that integral operator? So let's first consider the case of the Volterra operator. So that's where the upper limit of this integration is t, the independent variable. So what's the approach we're going to use? Well, I already said we're going to expand our solution as a Legendre series on 0t. But what we're actually going to do now is do the same thing for the kernel. Right? So this guy here is some function of k minus s. So it's expanded as a Legendre series, and then I'm going to substitute that into the operator. And again, if we assume that the kernel and the solution U are smooth enough, so again, Lipschitz continues to be enough, I can pull my summations through the integral sign, and we end up with this expression. And we would like to be able to express this itself, the result, as again a Legendre series. And why do we want to do this? Well, again, we want to equate coefficients at the end of the day. We want to, at the end, we have a Legendre series coming out of our left-hand side. We want to equate that with the coefficients on the right-hand side, and that will end up with a linear system we can solve for the coefficients. But the question is, how do we get these guys here, the coefficients of the result of computing this convolution? Well, fortunately, Alex and I had a paper in 2015 which showed how to do that. You end up, again, with some linear operator, V. The matrix, or the operator we end up with, is going to depend on the coefficients of the kernel, which it should do, but it is linear, and then multiplies the coefficients of the solution U. So it was a little bit tricky to show, but we managed to show how to compute this matrix here. And what you can also show is that if the kernel is a polynomial, then this thing itself is banded. So if the kernel of our integral operator is a polynomial, or it can be well approximated by a polynomial, we're again going to end up with a banded operator, which is one of the ingredients we needed in our ultraspherical method. So that was the Volterra operator. What about the Fredholm operator? Right here, it looks the same. The only difference is we've changed the upper limit of integration into a t, a capital T rather than a small t. Right? So now we're integrating over the whole domain. And we don't need to go through the details, but the key thing is that one can write a Fredholm operator as a Volterra operator. So this is exactly the same thing we just saw on the previous slide. Plus, well, whatever's left, right? We're integrating from 0 to t and from t to big T. And it turns out this guy that's left over, you can also write as a different form of a Volterra operator. I'm not going into the details, but you can do that. And we can use the same approach as before, and we end up with this. So here now we can end up with a infinite dimensional operator, which gives me the coefficients of this Fredholm operator, acting on the Legendre series. And all it is exactly the same matrix V we had before, from the Volterra case, plus a slightly shifted version of the same thing. So again, the key thing is we end up with a banded linear operator that we can include on our right-hand side to approximate this Fredholm operator. Okay, so now we have all the ingredients we need to solve that integral differential equation. The left-hand side we're going to deal with by using the ultraspherical method, but the Legendre version. And the Volterra operator or the Fredholm operator, we're going to use those operators we just derived. And so if we put it all together, we discretize these, we end up with this matrix. This is the one that comes from the ultraspherical differentiation of the ultraspherical representation of the differential operator. This is the Volterra matrix we just derived, and here's a banded linear system we have to solve. So we enforce the boundary conditions, we end up with an almost banded linear system, that's fine, we can still solve that efficiently. We truncate, yeah, and then we can solve for the coefficients of the solution. And since it's bounded, we can solve in linear time. The same thing for the Fredholm version, we just use the Fredholm version of that operator rather than the Volterra one. Yep, and we get a similar approach for higher order derivatives and non-constant coefficients. Okay, just to very quickly show you an example on how simple this is, all we need to do is construct those matrices on the previous slide, put them all together, and solve the linear system. That's basically what it's. Here's a picture of what that looks like. The key thing to focus on is that the convergence is fast. So here, this is a linear log scale. So the error is going down very quickly. And the key thing to notice here is that the matrix we end up with is almost banded. Right? It's banded near the diagonal, and we have just one dense row at the top of the matrix. Okay, so that was step 3. I realize I'm running out of time, so I'm just going to very, very briefly mention what goes on for fractional differential equations, or maybe I just spend some time saying what a fractional derivative is. So the first record of fractional derivatives was in a letter by Leibniz by L'Hopital, I think, to Leibniz. So Leibniz at the time was introducing his version of calculus, competing with Newton. And L'Hopital got wind of this, and he asked, well, what happens if you take a fractional derivative? In fact, he was interested in the half derivative. Leibniz was talking about dn, dx to the n, and L'Hopital asked what would happen if n was equal to a half. And here's a quote from the return letter. He said that this half derivative was an apparent paradox from which one day useful consequences might be drawn. And this has turned out to be true. So the past 300 years, there's sort of been theoretical approaches to what fractional derivatives might mean. But maybe in the past 20, 30 years, people have really been using these things for more applications. So in particular in epidemiology and finance, these things correspond to non-Gaussian random walks with heavy Hale distributions. So that's kind of a diffusion process where you have every now and then there's a very large jump in the diffusion, which can model, as you can imagine, various different things. What's the mathematical intuition for this? Well, think about what the nth derivative of x to the m would be. Well, we could all work out that it was this, right? This is the nth derivative of some power of x. But what's the generalization of a factorial? Well, it's a gamma function. So where we have a factorial here, if we replace it with a gamma function, we now might have something which we could think of as being a fractional or rational derivative or irrational derivative of some x to the m. If we had let n now not be an integer, but rather be some fraction. Similarly, we could think about repeated integration, right? So this formula here would give us the nth integral of some function f. And again, well, if we replace this factorial function with a gamma function, we could end up with maybe something which might represent a rational integral of the function. Okay, so it turns out that that is what we do take as the definition of a rational integral. Here, if I want the muth integral of some function f, it can be defined by this integral. And it turns out that it sort of behaves as we expect for certain special classes of functions. In particular, if you integrate a monomial, you end up with this, which if you let nu be an integer, gives you back what you would expect. Similarly, for exponentials, if you do the muth integral of an exponential, you get something that, again, is consistent with the integer definition. And also, if you do the muth integral of a trigonometric function, you get something which is also consistent with the integer definition. I'm just going to mention one more thing. The key thing for us, she and I, we managed to show that if you take the half integral of a Legendre polynomial, what do you end up with? You end up with, well, it looks like two Chebyshev second kind polynomials, but they're weighted with the square root of 1 plus x. But that's no problem. Similarly, if you took that kind of basis, the square root of 1 plus x times the Chebyshev polynomial, if you do the half integral of this, you end up back with a Legendre polynomial series. So what's the key thing? Well, thinking about the ingredients we needed for our ultraspherical polynomials, what did we want? We wanted bounded operators, and that's clearly what this is, right? If I took an integral of a series in Pn now, I could write it as a bounded matrix times a series in Un. And similarly, if I had a series in square root of 1 plus x times Un, I could write it as a bounded matrix times a series in Pn. And these are precisely those matrices here. So final thing I'll say, what's the approach to solving maybe an equation like this, right? We have, this is an apolinitric equation, here's a fractional derivative of solution u. What's the approach? Well, we expand our solution as a linear combination of Legendre polynomials and these weighted Chebyshev polynomials, and we end up with a linear system that looks like this. The key thing is both of these, or everything in sight here is a bounded matrix, so we end up with a nice discretization that we can solve very quickly. It turns out you can even rearrange the coefficients. In this case, you end up with a tridiagonal matrix, and you get geometric convergence. Okay, I'm just going to skip through. We can do the same thing for half-integer order derivatives, and here are some examples there. So I just want to summarize what I've been talking about. In each of these cases, both for the differential equations, the integral differential equations with the convolution kernel, and the fractional differential equations, were all the things we needed. Well, if we could take the linear operator that we had, so that might just be a derivative operator, it might be an integral operator. If we could express it as a banded operator between two or more ultraspherical polynomial spaces, and that's what we did in each of those cases. And if we also had a banded conversion operator between the spaces that we were working with, combining those two things together, it gave us a fast spectral method. Means that with banded or almost banded matrices, which you could quickly solve, and then get accurate approximations for the solutions to the ranges. And we saw that, as I said, for ordinary differential equations, integral differential equations, and fractional differential equations. There's some things I didn't quite have time to talk about. So non-constant coefficients, it turns out that's almost no problem. You can also write those, if these things are polynomials, we can write them as banded operators. I only briefly spoke about half-order derivatives and half-order integral equations. It turns out we can do rational order cases too. The expansion to partial differential equations is no problem. The real problem is nonlinear problems, nonlinear differential equations. The problem is that you end up with dense matrices when you do that, but that's maybe a topic for another day. So I think I'll finish there. I think leaving some time for questions. Thank you for your attention, and that's all.
Well, thank you. Thank you, Nick, for a very interesting talk. All right, water.
That's a lovely presentation. So in this particular presentation, we're performing a treatment of differential equations using very specific bases. Now, you gave reference to Jacobi polynomials, but now Jacobi polynomials are a special case of the hypergeometric polynomial, the hypergeometric series.
Yeah.
Now, the problem with hypergeometric series is they grow very, very quickly. So if you rewrite things in a certain way, if you're lucky, you get some sort of nice convergence. Now, hypergeometric equations, whether they be the hypergeometric series or hypergeometric differential equations, have an interesting pole structure. And so, as soon as you're expanding in terms of any polynomial, you can't, you're no longer sensitive to any sort of pole structure. So if you have any sort of behavior which looks like 1 over x, you can no longer treat it nicely in the region near where x goes to 0. So how do you treat these kinds of edge cases in your problems?
So maybe you're talking about the situation where the right-hand side would be singular in that case?
Yeah, yeah, some kind of singularity somewhere.
Yeah, I'm not looking at those kind of problems. So here I'm really focused on simpler cases, in particular where the solution is analytic, which is again quite specific. But in those cases, we know we can do really, really well. We get this exponential convergence. There are approaches people have looked at where you include singular terms in the basis to try and deal with those singularities. So that's not really what I'm focusing on here.
Thank you.
Thank you.
Gideon?
Yeah. Thanks for the nice presentation. So my question is this. To find the coefficient of series, you have to solve a linear system. So which means that this matrix has to have finite entries. So how do you get to determine of what extent? Of course, the solution depends on how many terms of the series you take. Then we talked about truncating the series. The code that determines how many of the series coefficients you have to be able to determine from solving the linear system. So how do you determine the truncation?
That's a good question. You can either guess, you can choose a particular size, you can solve the linear system, get the result, see how well you did. And if you're solving in linear time, that's not too much of an issue. There is another approach, I didn't really talk about it, called adaptive QR for these almost banded linear systems. So what you're kind of doing there is you avoid truncating. You sort of solve all the way down as you're going along, and you can sort of each time you do a step of this QR factorization, you can get an idea of how small the residual might be, and then stop when you need to. So adaptive QR factorization is the key phrase.
So does it mean that you always have to guess, truncate at a particular point, solve it, then take more times, solve it, and see the kind of error you get?
That is one approach, but this adaptive QR avoids that. They talk about solving the infinite dimensional linear system, so you kind of avoid truncating in some sense. So there are approaches to avoid truncating. I just mentioned truncation for simplicity.
Lastly, the last problem you showed has a singular kernel. The last integral equation.
Yeah, the fractional differential equation. So let me go back.
Yes, that's a singular kernel. So how do you avoid the singularity in the kernel?
So it's an integral singularity. The basis deals with it. So it just turns out to not be a problem. If it was a pole or a higher order singularity, then it would be a problem. But this is integrable, and if you integrate this thing, you end up with a branch cut on the left-hand side. But that's dealt with in my basis, right? So if I integrate this thing, I end up with a branch cut, a finite value branch cut, and my basis can deal with that. If this was x minus t to the 3 over 2, we'd have a problem. But maybe I could also include something in my basis which contained that, and then it would be fine. Is that okay?
That's fine. Thank you.
Thank you for your questions.
Any further questions? Well, Nick, we don't have any further questions here. I'd like to thank you again for a very nice talk.
My pleasure.
Thanks a lot.